On June 12, 2025, Air India flight AI-171 cleared the loading bays at Sardar Vallabhbhai Patel International Airport. Exactly 34 seconds after lifting off, the Boeing 787 Dreamliner crashed into a residential district. This data plot maps the 34-second flight arc. The plane reached a maximum altitude of 625 feet before entering a sharp, unrecoverable descent. At the exact peak, flight data captured the pilot's final transmission: thrust not achieved. Currently, the U.S. National Transportation Safety Board and India's Air Accidents Investigation Branch are extracting the recovered black boxes. However, the physical external telemetry surrounding the crash is already accessible. The 34-second duration and the pilot's report of a thrust deficit shift the focus away from routine steering errors. We are looking at signs of a systemic failure that occurred almost instantly upon rotation. Modern aviation is built on the engineering principle of redundancy. In a fly-by-wire aircraft like the 787, physical controls are replaced by electronic interfaces, meaning a single, localized severed cable or electrical glitch cannot cause catastrophic failure. The Dreamliner's architecture isolates risk. It features multiple, physically separated electrical generators and backup hydraulic lines designed to cross-compensate if one sector takes damage. To comprehend how AI-171 fell out of the sky, we must deconstruct the external visual evidence and trace the shutdown back to its origins. We will bypass the emotional recounting of the tragedy. Our focus here is entirely on forensic engineering and the mechanics of system failure. Reconstructing this event requires identifying how a modern airframe's primary power and backups could both be neutralized before the landing gear could even be retracted. Investigators don't have to guess the physical state of the aircraft upon takeoff. Civilian mobile phone video and airport CCTV footage captured the exterior profile of the plane milliseconds before impact. This 3D model compares a standard takeoff configuration with the first anomaly captured on video. AI-171's wing flaps were fully retracted. During takeoff, flaps must deploy downward to increase surface area, generating lift and managing drag. Without them, the plane struggles to climb. The footage isolates a second critical anomaly. 30 seconds into the flight, the aircraft's landing gear remained fully deployed outside the hull. Retracting the massive mechanical struts of the landing gear requires a massive surge of baseline hydraulic and electrical power. Leaving them deployed indicates that the aircraft lacked the energy required to complete the cycle. Combining the retracted wing flaps, the deployed landing gear, and the pilot reporting zero thrust, we isolate a definitive forensic signature. The crew experienced an immediate and profound loss of flight system control the moment the wheels left the runway. The civilian video reveals a final critical piece of visual and acoustic evidence. Just behind the landing gear, a small object is visible extending from an underbelly hatch. Based on its distinct shape and localized propeller sound, aviation engineers identified this object as the ram air turbine, or RAT. This schematic illustrates the ram air turbine. It automatically deploys during total power loss, relying on the aircraft's forward airspeed to spin and generate baseline electrical and hydraulic power. But at just 625 feet, AI-171 lacked the velocity required to power the control surfaces. The 787 is equipped with auxiliary power units that serve as primary electrical backups. The problem is that these units require up to 90 seconds to fully boot up and sequence power back to the grid. The deployment of the RAT is physical proof that the primary power grid died completely. Its failure to save the aircraft proves that a 34-second window between takeoff and impact is simply too short for any automated emergency failsafe to activate. The external telemetry leaves investigators with two leading technical hypotheses for the total power loss: fuel contamination and total electrical failure. The first hypothesis points to chemical contamination in the fuel supply, such as water, microbial growth, or diesel exhaust fluid, choking the delivery lines and triggering a simultaneous dual-engine failure. Flight logs show that refueling AI-171 in Ahmedabad took 42 minutes, slightly longer than standard. Additionally, a similar fuel contamination event crippled both engines on a Japanese 787 in 2019, making this a statistically valid path of inquiry. This split-screen schematic compares the physical fuel delivery manifolds against the alternative hypothesis, the collapse of the aircraft's variable frequency starter generators. If the electrical grid fails, the fly-by-wire engine controls lose power. The digital connection to the cockpit severs, resulting in zero thrust. Passenger footage recorded before the aircraft left the gate correlates heavily with an electrical grid problem. Passengers documented completely non-functioning air conditioning, dead entertainment screens, and flickering cabin lights. Both hypotheses fit the tight 34-second timeline of the crash. However, the pre-flight cabin anomalies strongly tilt the mathematical probability toward a cascading, pre-existing failure within the electrical grid, rather than bad fuel. To find the root cause of an electrical collapse, we have to look past the final 34 seconds of flight and examine the 11-year operational history of this specific airframe. Delivered to Air India in January 2014, AI-171 rolled off Boeing's Charleston assembly line during a period plagued by severe manufacturing deviations. Former quality managers and engineers from the Charleston plant provided explosive testimonies to federal regulators regarding the assembly of Dreamliners during this exact window. They documented mismatched parts and metal debris routinely left inside sensitive wiring housings. Once delivered, the maintenance of this aging fleet fell to Air India Engineering Services Limited, a state-owned entity tasked with servicing highly complex digitized aircraft. Audits conducted in the years prior to the crash revealed systemic negligence within the maintenance organization, including documented instances of falsified audit reports and entirely skipped safety checks. An isolated wiring short caused by factory debris is a minor glitch, but when a manufacturing defect is compounded by a decade of skipped safety inspections, it degrades the aircraft's redundancy until that minor glitch cascades into a fatal power failure. The visual deployment of the ram air turbine provides a critical diagnostic marker, indicating a total power loss while the aircraft was at low altitude. Whether triggered by contaminated fuel clogging the manifolds or an electrical grid collapse severing the digital engine controls, the aircraft was starved of thrust. The failing cabin air conditioning and dead monitors prior to takeoff were early symptoms of a highly compromised electrical architecture. A decade of documented factory quality assurance warnings, combined with deep systemic maintenance negligence, created the exact physical conditions required for this failure. The trajectory of AI-171 was the result of a linear chain of neglected systemic risks, where manufacturing defects met maintenance oversight. The loss of AI-171 exposes a brutal paradox in modern aerospace engineering. Redundant failsafes are completely useless if the aircraft lacks the time or altitude to deploy them. Automated emergency systems, no matter how advanced, remain entirely reliant on the baseline manufacturing integrity and rigorous daily maintenance protocols that support them. When those protocols are treated as optional, the margins of safety evaporate. When organizational oversight degrades and quality assurance is systematically bypassed, catastrophic mechanical failure ceases to be a tragic accident. It becomes an engineering inevitability.